We will now study compact self-adjoint operators. So H Hilbert space and T belong to LH. We say T is self-adjoint if T equals T star, and we have already seen the following thing. So T self-adjoint implies sigma T is contained in R, and in fact we have also seen that sigma T is contained in M, capital M, where M is the inf of TVV, norm V equal to 1, and capital M equals the sup of TVV, norm V equal to 1. And you also saw that M and capital M belongs to sigma T. This was done in the exercises of the Hilbert space chapter. Okay, so corollary, T in LFH self-adjoint and sigma T equal to singleton 0 implies T equal to 0. So proof, we saw that, so if sigma T is 0, that means M equals capital M equal to 0, and therefore you have that TVV equal to 0 for all V, and this implies, since H is over the complex numbers, we saw that it's not true for the reals, T equal to 0. Okay, so this we have. Okay, so with that observation, we have the following important theorem. Let H be a separable Hilbert space and T belongs to LFH. Be self-adjoint and compact operator. Then H admits an orthonormal basis consisting of eigenvectors of T. Okay, so, and of course it's obviously countable because H is a separable Hilbert space. Okay, so proof. So let sigma T equal to singleton 0 union lambda n, n in capital N. Okay, set lambda naught equal to 0, and then lambda n, n in capital N are all eigenvalues of T, all eigenvalues distinct of T. So we said E naught equals null space of T and En equals null space of T minus lambda n times I. Okay, then what do you know about E naught? E naught could be singleton 0, so 0 could be less than or equal to dimension of E naught, and E naught could also be infinite dimensional, so this can always happen. On the other hand, 0 will be strictly less than dimension of n of En, and that will also be strictly less than infinity for all n in N. Okay, so the spaces En, n greater or equal to 0 are all mutually orthogonal. Why is this so? Let n not be equal to m. So you get u in En, v in Em. Okay. So Tu will be lambda n u and Tv will be lambda m times v. Okay. So then if you take lambda n times uv, this is equal to TUV. This is UTV because T equals T star, and that's equal to lambda m times v, and lambda m is real, so it will come out u times v. Okay. So lambda n minus lambda m uv equal to 0, and this is not 0, and therefore you have that uv equal to 0. Okay. So all these spaces are mutually orthogonal to each other. So now let F be the space generated by union En n greater equal to 0. Okay, so you put all these spaces together and you have. So claim F is dense in H, which is equivalent to saying F perp equal to singleton 0. Okay. Because if you have a vector vanishing on F, then it vanishes everywhere. That is the Hahn-Banach way of showing a space is dense, and therefore showing F perp equal to 0 is equivalent to showing F is this. Okay, so clearly TF is contained in F because any eigenvalue is the same, so it will be in the same En, and linear combinations will also be. So TF will be contained in F. Now if U is in F perp and V is in F, you have TUV equals UTV. Now V is in F, so TV is also in F, and this is in F perp, and therefore this is equal to 0. So this means that T of F perp is also contained in F perp. So now you take T naught from F perp to F perp. T naught equals T restricted to F perp. Okay, so this T naught is obviously self-adjoint and compact. So let lambda tilde not equal to 0, lambda tilde belong to sigma of T naught. So it's a self-adjoint compact operator. F perp is closed, so it's a Hilbert space in its own right, and therefore always the perp is always closed, so it's a Hilbert space in its own right, and you have a compact self-adjoint operator in it, and therefore it will have a spectrum. So assume it has a non-zero element in the spectrum, then implies it's an eigenvalue because it's compact. Implies there exists U in F perp, U not equal to 0, so such that U lambda tilde U equals T naught of U, but T naught is same as TU. So implies that U is an eigenvalue, so sorry, lambda tilde is an eigenvalue of T also. Implies therefore, but we have lumped all the eigenvalues together in the space F, that means U belongs to F intersection F perp, and U is not equal to 0, which is a contradiction. Okay, you cannot have that. Okay, so this implies that sigma of T naught is singleton 0, and by our earlier corollary we have that T naught is in fact equal to 0. So that means this implies that F perp is contained in the null space of T, and null space of T is contained in F. This is E naught in fact. Okay, and therefore this implies that F perp equal to singleton 0. That's the only way it is possible. Okay, so now E naught, if E naught is non-zero, then it is finite or infinite dimensional closed subspace of H, and therefore implies it has a countable orthonormal basis. Each n greater equal to 1 is finite dimensional, implies it has a finite orthonormal basis. Then the union of all these orthonormal bases is an orthonormal basis for H, since f perp equal to 0, that is f is dense. Because if the union is orthonormal is clear, if x is orthogonal to all of these basis vectors, then x is orthogonal to the space f, and then we saw that f perp is 0 since f is dense, and therefore it is a thing. So this proves that you have an orthonormal basis for H. So next we will look at a variational characterization of the eigenvalues.